We have been talking about matter, and then we talked about phases of matter, and now we're going to talk about phase changes. So we're talk about how things go from one phase to a different one. But before we do that, what is a phase of matter? A phase is the state that matter is in. So it can be a gas, it can be a liquid, it can be a solid. And so phase changes means it's changing from one to the other. Before we talk about phase changes, we have to talk about the difference between physical changes and chemical changes. So physical changes are changes that happen in the properties. So let's say temperature or volume or pressure or what it looks like. Changes in that without creating a whole new substance, without changing the molecules themselves. For example, if we dissolve salt in water, it still stays salt and water. We don't have a completely new thing. It's salt and water. They look different. The salt, you can't see all the individual little crystals, right? But it's not a new thing. It's still salt and water. These changes are usually easily reversible. So could we reverse putting salt in water? How would we do that?
You could boil it.
Yeah, exactly. You would boil the water, you boil it all off, then you're left with salt, right, in the bottom. It's reversible. Mixing salt and water is reversible. Physical changes are typically reversible fairly easily. If I took a piece of paper and I shredded a piece of paper, now I have a bunch of pieces of paper. It's not something different. It didn't suddenly turn into gold, right? It's still paper. It just looks different than it did before. And I could take the pieces and tape them or glue them back together or whatever. Then I would have my piece of paper back. Would it look exactly the same in that case? Probably not. So that might be not the best of examples, but I can reverse it. I can undo the change. For chemical changes, in a chemical change, it actually changes the type of molecule that you're working with. So if I take hydrogen and I take oxygen and I force them together, that's going to create water. And water has very different properties. It has a different chemical structure. It's going to act completely differently than hydrogen or oxygen on its own. I have a completely new thing. It actually forms new substances, a new type of molecule. Chemical changes are often not easily reversible. If iron rusts or if you burn wood, you can't really unburn wood, right? And you can't turn the rust back into iron without having a chemical reaction to undo it. So it's a chemical reaction. So that's the difference between chemical changes and physical changes. So in talking about phase changes, we need to understand that phase changes are a type of physical change, not a chemical change. If we're changing something to a completely different thing, that's not a phase change. For phase changes, a phase change happens when matter switches between a solid and a liquid or a liquid and a gas. And that happens because of a change in temperature or a change in pressure. And phase changes are a type of physical change because we can undo them, right? We can take water and put it in the freezer and it becomes ice, and we can take it out of the freezer and it becomes water again, no problem, right? We know from your experiment that you guys designed, you can take water vapor and turn it into water, right? You collect it and condense it. So that is a physical change, not a chemical change. Here are different types of phase changes. So the one there on the top left is freezing, when water or any other liquid turns into ice or a solid. So when a liquid becomes a solid, we call that freezing. Now, we think of it as water most of the time, but if you think about it, look around us. Look around you in your room. There are lots of things that are solids, right? And we're not at the freezing temperature of water. If you have water sitting on your counter, it's not going to freeze, but all these other things are frozen. So, for example, my countertop is made out of rock. So it is past, it's below its freezing point. If I heated it up enough, it would turn into liquid, right? Think of a volcano and the lava coming out of the volcano. That is really, really hot. It takes a ton of heat to get to your melting point, right? So we are already at the freezing point of rock, even if we're not at the freezing point of water. The freezing point is different for each thing. So we have lots of things around our house that if you heated them up enough, they would melt, but right now they're in their frozen state. Think about when you're going from the lava that's melted to the lava that has solidified into rock, that's its freezing point. So on the one hand, you have freezing. That's where your liquid is turning into a solid. At that temperature, you're gonna have half of your things going from a liquid to a solid and half the things going from a solid to a liquid, because your melting point and your freezing point are the same exact temperature. So for water, for example, 0 degrees Celsius is the freezing point of water. So at that, you have some water that's changing to ice and some ice that's changing to water at about the same rate, so it's going to stay about the same. If you go just over it, then everything's going to start to melt. And if you go just under it, everything's going to start to freeze. And I mean just under. The only time it's at an equilibrium, while the same amount is freezing and melting, is exactly 0.0. So if we're going from liquid to solid, that's called freezing. If we're going from solid to liquid, that's called melting. So in our example there of the ice, when ice changes into water, when it's heated, that is melting. But the freezing point and the melting point, that temperature is exactly the same. So then if we add more heat, we go from the melting and go on to vaporizing. So at zero, just above 0 degrees, our ice starts to melt. If we keep going and going and going until 100 degrees Celsius, that is the boiling point of water. Other things have different boiling points, right? So for example, oxygen, if we wanted to get oxygen solid, we have to go way lower in temperature, right? So it has a different vaporization point or boiling point where it goes from a liquid to a gas. So think about, you took your water out of the freezer, it was ice, now it melted into water. Now we're gonna put it in a pan and heat it up, and it's gonna vaporize or turn into water vapor. So that is called vaporizing. It's the boiling point, and that's where it starts to turn from liquid into gas. But then at that same 100 degrees Celsius, we have what is condensing. So you have our vapor turning into liquid again. So again, your boiling point and your condensation point are the same temperature. When you're exactly 100 degrees Celsius, the water is going to be, some of it's going to be changing into gas and some of it's going to be turning back into the liquid at an equilibrium. If you go just above it, then all the water is going to start vaporizing. If you go just below it, everything's going to start condensing. Just remember that it's not just water. I'm showing an example of water, but everything has a boiling point or a melting point. So for example, I think we talked about that water is the only thing that's naturally existing commonly on Earth in all 3 states. But we talked about the fact that mercury, which is a liquid at room temperature, actually can boil and turn into gas if it's really hot, or it can freeze and actually become solid mercury, but it has to be super, super, super cold. So it's not just water that can go through those phase changes. Everything can go through those phase changes. There are some things that do a direct transition. So I don't know, have you ever messed around with dry ice?
I have once.
Okay. It's really cool. If you ever get a chance to do, just be really careful because it can give you frostbite. But if you take dry ice at normal temperatures and you pull it out of whatever container it's been in, it doesn't stop at the liquid stage. If you had it at just the right temperature, you could get it to a liquid, but at normal room temperature, you pull that dry ice out and it just starts to give off stuff that looks like smoke, and that's the gas coming off. It goes straight from a solid to a gas, and that's called sublimation. So our example here is dry ice. So solid dry ice turns straight into a gas without melting first, and that's called sublimation. Then if we do the opposite, going straight from a gas into a solid, and our example there is if you ever have on your windows outside, or you take something like a glass outside and it's really cold, it won't stop and turn into a liquid and then freeze. The water comes straight from the air and immediately turns into a solid or turns into those crystals, if you've ever seen that frost. So it forms directly from water vapor in the air without stopping to become liquid first. and that's called deposition. And those are two direct transitions where it doesn't go through the middle stage of liquid. So liquids are middle stage if we go through from one to the other, but this one's skipping the liquid stage. So sublimation from solid to gas, deposition from gas to solid, but that's much more rare. So I want you to take a second and write down these terms in your notebook. So this is phase changes. Solid to liquid is called melting. If you go further and go liquid to gas, that's vaporizing. The opposite direction, if you start with a gas and go to liquid, it's called condensing. From a liquid to solid is called freezing. And then our two that skip steps, from a solid straight to a gas is called sublimation, or from a gas to a solid is called deposition. My hair is back, ready for the experiment. Anytime you're working with a flame, it's a good idea, even though my hair is not super long, it's always a good idea to have your hair pulled back if you're working with a burner. So let's gather the things that we will need for this experiment. First, you'll need a 250 ml beaker if you're doing it this way, or you will need a pan. You will need your burner and a stand. For that, you'll also need your fuel. If you're using a burner, please make sure that it's full because this is a very long experiment and you don't want to run out of fuel partway through. So I'm going to go ahead and top mine up. If you're using a burner, you're going to need a lighter as well. You're also going to need a thermometer. I am using a lab thermometer. You could also use a meat thermometer, a candy thermometer, something like that. I'm also going to be using a stand, partly because I want you to see what scientists actually use, and partly because it really is easier. It's going to change the temperature if you're getting closer or further away from the flame. So I want to keep my thermometer as close as possible to the same spot. So I'm going to go ahead and set this up like it will be when I have it going. I'm going to turn it around. Now I'm going to put it in there because this is going to go in between this rubber piece. That is where I want it, except I want it turned where I can read it easily. I'm going to be reading the Celsius scale, so I want to make sure that I can see that Celsius side over here. I'm going to have my burner underneath, and that's going to be my setup for the experiment. Besides this, we will need water, as well as later on we'll need salt. You'll need your chemistry notebook. Then we also need ice as well. Here is my bowl of ice. You're also going to need a timer of some kind because we're going to measure at 1 minute intervals. So let's get started. Just as a quick safety reminder, you never want to put your glassware straight on your stove. Use that only like over an alcohol burner. If you're using your stove, be sure to use a pan. Along that same vein, you want to make sure that you don't put any other kind of glass on here. It needs to be a beaker that is made to handle heat. So an actual beaker from a science place that is made to handle heat. So don't put like a drinking glass or anything like that on your burner or on your stove either. This is one of the longest experiments we'll be doing this year. So if you're not able to hang in there the whole time or you need to fast forward a little bit, that's okay. But we're going to be taking notes as we go. I want you to draw your apparatus, whether it's like this or your stove, label it, put how much of each thing is on there. So I want you to draw a nice picture. You can title this page Phase Changes. Don't forget to put that in your table of contents as well. Also be sure to leave room because you're going to be taking notes of each of the times and the temperatures twice. And then we're actually going to create our graph on the computer and I'll show you how to do that. Then we're ready to get going with our experiment. So I'm going to fill up my beaker with ice, or if you're using a pan, fill that up with ice. So I've got my beaker full of ice. Then after that, you're going to pour water over the ice until it covers it. So all the way to the top. Your ice will actually start floating, so just fill it till it starts floating and is filled up pretty well. Now we're gonna let it sit so that it gets a consistent temperature throughout. So we're gonna let it sit for a little while we do some other things. So we're gonna get the burner ready in case you haven't used one before. So it probably should come with a stopper in there to keep the alcohol from evaporating. So you will need to pull that stopper out. Then you hold the top and bottom and twist and pull that off. If you don't already have alcohol in it, you want to put alcohol in it, not all the way full because you don't want it to drip out. Then once you've filled it with alcohol, you put the lid back on and screw it back on. And then it's ready to go. And then you'll put your stand over it. When you go to fill up your burner, be sure to make it pretty full because this is a long experiment and you don't want to run out of fuel in between. It will mess you up. So make sure that you have plenty of fuel in there. Then I'm going to light my burner. I'm going to move a few of these things out of the way for just a second. So I'm going to use my lighter. I'm going to stick it right where those two holes are. That's what's letting the alcohol escape. That'll catch fire. If this is your first time to use it, or if it's been a little while, it might take a minute for it to catch because it takes a while for the alcohol to get up the little pipe there. I got a little bit of alcohol on the outside of mine, so that's got to burn off for a second. Now that's what it should look like. So now we're ready to put everything together. Now that this has been sitting for a couple minutes and should have a consistent temperature throughout. If you're using a stove, make sure that you choose the right size flame or the right size burner if it's electric for your pan. You want to make sure that it doesn't go outside of the size of your pan. It'll go up the sides and actually melt your handles if you have those, or just it's not safe. It'll get the sides too hot. So just make sure that that stays underneath your pan. But I'm using the burner, so I'll show you what that looks like. I'm actually going to set my thermometer toward the top because I know from past experience that if I put it toward the middle, it catches too much of the heat from the burner and makes it not act the way it's supposed to. I'm setting it right toward the top. I don't want it out of the beaker, but I want it as close to the top as I can without getting it out of the beaker, the red part of my thermometer. So I'm going to leave it there. I'm waiting for it to get to where it needs to be, or at least close. Thermometers aren't super exact, so it can be off as much as 2 degrees. So once it stays at the same place for a while, you can say, okay, it's at 0.5 degrees Celsius. I know that my thermometer is off by about 0.5 because we know the freezing point of water is 0. So ideally, if your thermometer is perfectly calibrated, it will be 0 degrees when the water is frozen or when there's ice in the water. That's not always the case. So I'm going to let it sit till it stays in the same spot for a couple of minutes, just to make sure that I know how my thermometer is calibrated and that it has gone down from room temperature where we started to actual temperature of the water. Right now it's showing about 1.1 degrees Celsius. You should be able to, on anything that's an analog scale like this, obviously not with your digital scale because it gives an exact readout of what it's able to measure, but with something like a thermometer that has the analog scale, you should take the measurement 1 decimal point beyond what your scale shows. On my thermometer, the biggest lines are 10 degrees apart, and between those there's a 5 degree mark, and then they're marked every degree. That means that I should be able to estimate 1 decimal point beyond that and say it's 1.1 or 1.2. Obviously that won't be exact, but it'll give me a closer estimate than it was 1.4 versus 1.1. There's a difference there. So I want to make sure that I'm catching it as close as possible. So you estimate to 1 decimal place beyond whatever your scale measures. Mine's been sitting at 1.1 for a while, so I think that's a pretty good indicator of that is how much my thermometer is off by. That should be the temperature of the water with the ice in it. One thing that I didn't say before, you do need something to stir with, so I'm going to be using a glass stirring rod. You can use a spoon, whatever you need. If you're doing it in a beaker, I would suggest not a spoon, but like a knife or something, because you need to be stirring that around, because if not, you're going to get just the temperature of that one spot of the water and it's not going to be super accurate. So you need to be stirring as we're waiting. during those 1 minute intervals. So I'm still letting mine go down just a little bit just to make sure it's going to stay at a single spot. My thermometer is showing about 1 degree Celsius and it's sitting there pretty steadily with this ice water. That means that probably my thermometer is off by about 1 degree Celsius. I'm going to go ahead and estimate. Mine looks like it is right on the 1 degree line. So I'm going to say mine is 1.0. I'm going to relight my burner. Had to turn it off there for a minute. Now I'm going to make a table and I want you to do the same thing in your chemistry notebook. So I'm going to draw a table. I'm actually going to draw two, one on the left and one on the right. If you hear funny noises, that's my burner making all sorts of sounds. Then I'm going to write minutes on the left of both of those and degrees Celsius on the right of both of those. On the left one, I'm going to write no. On the left, I'm going to make 2 tables and I want you to do the same in your chemistry notebook. So we're going to do 2 tea tables like that. One on the left and one on the right that we'll use later on. For both of those, I'm going to write minutes on the left and I'm going to write degrees Celsius on the right so I know what the numbers mean. Then on the left one, I'm going to say this is no NaCl, which is sodium chloride. That is our name for table salt. On the right one, I'm going to say with NaCl because we're going to repeat the experiment adding in salt. Now I'm going to go ahead and get my 1 minute timer ready. Now I'm going to go ahead and get my 1 minute timer ready. I'm going to move my burner under there. And I'm going to start my timer. And don't forget, we need to be stirring. While doing this, we're only going to stop stirring when we're taking our measurements. There's our timer. I'm going to check my temperature. Mine is showing about 1.9 now. I'm going to start stirring again, start my timer, and then I want to take down that annotation here. So my first measurement was at 0 minutes. It was 1.1 degrees Celsius. At 1 minute, it's 1.9. Then I'm going to go back to my timer and keep stirring. All right, I'm going to start my timer again. Go ahead and check my temperature. Now it's showing about 4.0 degrees. I'm going to mark that as my 2 minute time. And keep stirring. Most of my ice is gone at this point. I'm going to start another 1 minute timer. That is showing about 6 degrees. So I'm going to go ahead and write that down on my graph. It was right at 6.0. And we're still stirring. We're getting really close to all the ice being gone, so we should start seeing some big changes in our temperature pretty quickly. Okay, there's our timer. Let's start a new timer and check my temperature. We're about 10.1. All of the ice is gone at this point at about 14 degrees. All right, there's another timer. I'm going to start again, and I'm at about 18.9. What was supposed to happen, and what has happened in the past when I've done these experiments, it stays around 0 degrees until all of the ice is melted, and then it starts actually heating up the water. So I'm not entirely sure why it didn't work very well this time, but now that all the ice is gone, it's starting to heat very quickly. I'm wondering if I'm not being able to stir it well enough to make sure that the water at the top is the coldest. I honestly don't know what's happening. There's our timer. We're going to start another one, and we are at about 24.9 now. Now we're going to keep measuring until we start boiling. And I guess I should have thought that through. I didn't leave quite enough room at the top, so it's going to be swirling out a little bit as we start boiling, I'm afraid. There it is again. I'm going to start a new one. And now, oh, I can't see that one very well because of the deal, so I'm going to have to guess. It looks like it was right about 30. I'm getting ready to measure again. Start another timer. And now we are at 36.9. At 8 minutes, 36.9. If you only have a Fahrenheit thermometer, you should be around, whoop, here's your timer. Start a new one, measure the time. We're at about 42.1. If you only have a Fahrenheit thermometer, you should have seen that freezing was around 32. And our boiling point will be around 212. But for Celsius, 0 degrees is freezing and 100 is boiling. Which makes a lot more sense if you think about it. It would be based on water since it's something so common. Just a few more seconds before I measure again. Start our timer again. And now we're at about 47.9. About 15 more seconds. Okay, start another timer. And we are at 53.0. Since my thermometer was about 1 degree when we were in the frozen water, or the water with the ice, I'm expecting that my boiling temperature will be somewhere around 101. Start a new one. And now we're at 58.1, 58.0. My burner's very noisy. Okay, start another one and check my temperature. I'm about 63.5. That's a really annoying noise. Start another one. And now we're at 78.0. Yours may go faster, it may go slower. When I did this in a lab with a couple of lab groups, the flame from one group's burner was pretty different than the other one. And so one was going really fast while the other one was going comparatively slowly. Also, it'll be pretty different if you're doing a burner versus on the stove. So don't expect that you're going to be hitting the same temperatures at the same time. Okay, check it again, start a new timer. We're at 72.7. Sorry. Yes. Which means I realized that I read the other one wrong. It was actually 68.0. Sorry, I read that out wrong. Getting closer and closer, I can see some steam starting to come up. Let's try another one. I'm showing 77.8. We're getting a few bubbles at the bottom. That means that that water down there has actually gotten to the boiling point. What's at the top hasn't quite yet. So it's so much closer to the flame. There's another minute. We are right at 81, so 81.0. Down to about 20 seconds. Okay, the next minute. We are at right at 85.0. Getting really close now. Oh, there's our next minute. We are at 87.1. Start that timer again. Now we're at 90.1. It looks to me like because the bottom is starting to have a phase change to where the bottom ones are turning from liquid into gas, it's making the transfer of heat slower, because it's actually using most of the energy to change the phases rather than to actually heat up the water. And that's what we should have been seeing. We're seeing it at a funny time now because of the difference between the heat of the water at the bottom. There's another time. Now we're at 91.9. A lot of the heat is being used to change this water at the bottom from liquid to gas state. So less of the energy is going up toward the top to change this water's temperature. 10 more seconds. There's our time. Let's try a new one. We're at 93.9 now. Now that we're seeing that water at the bottom change phases, it'll be interesting to see what happens with the temperature, how fast it goes up now. Here's our next minute. And now we're at 95.2. About 5 more seconds. There it is. And we're at 96.4. 3 more seconds. There we go. We are at 98.0. Okay, here's our next one. We're at 99.0. You can see the bottom's already going pretty good. pretty much mixing itself at this point, but just to stay consistent, I'll keep mixing. Okay. Our next minute, we're at 99.8. Now you can see there's actually gas escaping at the top, so we have full boiling at the top already. So it shouldn't really change at this point. It should stay right about that 99.8, 0.9, somewhere around in there. I'm gonna keep going for another couple minutes just to make sure it doesn't keep going. Like I said, my estimate was that it should go to about 101 based on my calibration. We'll see if that's true. Okay, that was our next minute. We're still at 99.8. We'll do it one more time. If it stays at that, we'll know that we've hit our boiling point. What happens at that point is that the water no longer continues to heat. All of the energy coming from the burner, from the heat from the burner, is actually being used to change the water into gas at that point. And so it doesn't actually heat up the water, it just changes phases. And so we shouldn't see any temperature change. The water just starts evaporating until it's all gone. It won't actually change temperature. There we go. Yep, and we're still at that 99.8. So we are fully boiling now. It won't increase in heat anymore. I'm going to go ahead and write that down, and we'll be able to see 99.8. Just for fun, we'll go all the way to 30 minutes. Just to have a nice round number. 10 more seconds. All right. If anything, it looks like it's gone down just a hair, just from my moving it around probably. So we're about 99.5 at this point. All right. Now what we're going to do is break this down, and we're going to start over, but we're going to add salt. Please don't forget that this is going to be very, very hot. So handle with hot pads or beaker tongs if you have them. So I'm going to hold on to that. I am still going to use my hot pad because the stand is hot. I'm going to set it down here on this heat safe spot. Turn off my burner for right now. I'm going to let this cool down for just a little bit, and then we'll come back and do the experiment again with the salt. Now that everything has cooled down, we're ready to start the experiment again. I went ahead and added some fuel to my burner so that I'm sure not to run out. The first thing that we want to do for this one is we want to put 100 grams of sodium chloride, which is our table salt, in here. So I'm going to use my electric balance. To do that, I'm going to turn it on. I'm going to put the dish that I'm going to be measuring it out into on there. I'm going to hit the tare button so that it zeroes out. Then I'll take my salt, and I want 100 grams of salt. If you do not have an electronic balance, you can measure out 6 tablespoons of salt. A 100 grams is a lot. Like a lot, a lot. Oop, went too far, too far. I feel a little bit magic because it's 100.00 exactly. Okay, so there's my 100 grams of salt. I'm going to put that into my beaker. It was wet, so it stuck. 100 grams in my beaker. Then I'm going to add the water to it and mix. I don't want to fill it up all the way because I still need room for ice. I'm going to fill it up a pretty good part of the way. Then I'm going to use my glass stirring rod to stir that up. That is a lot of salt. You want to be sure to stir it up and get that in there before you put the ice, because the ice makes it a lot harder for it to dissolve. Now that I've got this stirred up, I'm going to actually pour this into a cup so that I can put ice in this and then add the water on top of it. So I have my salt water here. I'm going to fill this up with ice. So I make sure to have enough ice in there. To have a similar experiment. Then I'm going to make sure this is nice and stirred up. And pour it back over the ice. All right, now I'm going to put that, the thermometer, and I'm going to let it sit for a little bit so that we can get that thermometer back down. Since it was sitting at room temperature, it'll take a little bit for it to get back down to the actual temperature of the ice water. Now, we know, because of the way that we use ice to make the roads not slick, when there's ice or snow out there, that something happens to the freezing point when you add ice to things. Does it lower it? Does it raise it? We'll find out. You could think through logically what it should do, what the point would be of putting ice out on the street, but let's find out experimentally as well. So I'm going to wait till my temperature evens out and stays the same for a little while. Right now my temperature is showing about negative 10.9 degrees. Definitely different from my 1.1 where we started. We'll see if it stays there, if I need to let it go a little bit longer. Actually, as we sat here, it's gone down. So now we're gonna call it, well, it's still going down. I guess we'll wait a little bit. Now it's been sitting for a while and it looks like it's negative 11.5. So we're gonna put that as our starting temperature. So at 0 minutes, it's negative 11.5. I'm gonna go over and start my 1 minute timer and slide that burner under there. And remember, we want to keep stirring throughout the entire time. There's lots of condensation coming off, sublimation happening there at the bottom as that really cold water is being hit by that the heat from the burner. 10 more seconds. Okay, we're at about 10.1, negative 10.1, that is. At 1 minute, negative 10.1. The condensation's coming off the side and hitting that burner, and so it's sizzling. That's okay. About 15 seconds. Okay, there is our timer. And right now we are at about negative 7.5, about 2 minutes. All right, here's our next minute. And we are at about negative 3.2. Okay, here's our timer. Our temperature right now is right at 0.0. About 4 minutes, 0.0. We're now out of water. Oh, and there's our timer. We are at about 7 degrees, about, let's say 7.1. Now that our ice is gone, we should start seeing the temperature rise more quickly. That's why we had that big jump from 0 to 7. Okay. Now we're at 17.9. Now we're at 25.8. This next one's going to be tough because we're back under my plant. I have to do a little bit of guesstimating there. In about 10 seconds. There we go. Oh, no, it went above it. Okay, we are at 33.9. Got a ways to go still. Again, we're trying to see how the salt affects the boiling point. So you may have heard that some people like to put salt in their water because it makes the water boil faster. We're going to see if that's actually the case. So we saw already that, hold that thought. There's our next minute. Right now we're at 40.3. So we saw already that it lowered the freezing point, or the melting point as the case word, that's the same point, because it was able to go down below 0. So we were down at around -12. That means that the salt was able to lower the freezing point. There's our next minute. We're at 46.7. What that means is that the reason we put salt on the ice is that it lowers the freezing temperature, which means it has to get colder for that to freeze, which means that our roads won't freeze over at the same temperature. So if it's 32 degrees Fahrenheit or 0 degrees Celsius, it won't freeze if there's salt on it because it has to actually get down quite a bit lower. Depending on the type of salt, it'll be different. If we use table salt, apparently it would be about 10 degrees lower, 12 degrees lower. But that's why putting salt out on the roads or on your sidewalk or whatever will help with the streets and help it be safer. Okay, our next minute, we are at 53.5. So we'll see now how long it takes for it to start boiling. You take a guess. We call that a hypothesis. Do you think it will mean that it will boil sooner? Or will it take longer to boil? Or will it be the same? What's your hypothesis? There's our next minute. We're at 59.9. About 10 more seconds. Here's our timer. We're at 60, let's call it 66.7. Got a little crazy there. 15 more seconds. Here's our timer. We're at 72.8. You'll notice at this point, the salt that was still hanging around at the bottom when we had ice in there is all now in the water. The higher the temperature of the water, the more salt it's able to actually take in or dissolve, as we call it. So that extra salt that wasn't being able to dissolve in the cold temperature is able to dissolve now that the water's hotter. So if we were to add more and more salt, we could up to a certain point. We won't though. Don't want to mess with the experiment. There's our next minute. And we are at 67.9. Sorry, 77.9. And we're gonna have to draw a new table over to the side to add the rest of our times there. Good, starting before our minute's up. About 15, now about 15 seconds. So next minute. And we're at 83.2. 20 seconds left. Now we're at 87.8. 15 seconds left. There we go. Now we're at 91.6. Okay, you'll see we're starting to have phase changes down at the bottom, which again is part of why our changing in temperature is slowing down, because a lot of the energy is being used to change phase of the water at the bottom of the beaker. And so the temperature is changing much more slowly. 5 seconds. We're at 94.9. Ten seconds left. We're getting on up there. Not too much longer now. At 20 minutes, we are at 97.6. We're at 100.1. Got a lot of boiling going on at the bottom. Nothing on the top quite yet, so our temperature is going to continue to increase. Or I say it should. You'll see there's white collecting on the stand as well as on the outside of the beaker. That is the salt water that's come out, and the salt is the salt doesn't evaporate, the water has evaporated. There's our next timer. We are at 101.9. Again, we have boiling at the bottom. We'll see if we stay. It's getting further and further up, so we might not change temperatures. We'll see. Remember our last one went to about 99.5. 99.8 is highest point. I'm not sure why it went down there for a second. It's still going up though. Okay. At our next minute, we're at 103 even, 103.0. So it's interesting. The boiling point is still going up, but we did get there faster. Interesting. So we know already the first one was 99.8. Now we're all the way up to 103. And at least at last check, we were still climbing. We definitely climbed past the 99.8. That means that it actually raises the boiling temperature. But again, we got there faster. Let's see what happens now. 2 seconds. We're now right at 100.3 still. No, sorry, 103.0. We got 4 matching temperatures before we stopped last time, so that's what I'll try for this time. We'll see if it's gonna stay. Oh, it's still going up. Well, with the stirring, it's making it kind of sit right about there. So we'll see if we can get 4 temperatures right in that same spot before we stop. Okay, we're at 103.1. So it was the stirring that was letting it go up higher, or the not stirring. So that's 3, right about that same temperature. If this one's the same, we'll stop there. We're at about 103.9. So maybe we'll try one more just in case. I like the fun patterns it's making on the outside of the speaker. I'll show you here in just a minute. All right, 1 more minute. And we're still right at 104. We're going to call that good. Okay. 103.9 is actually what it is. We're staying right about there. So I'll take that off and show you. The fun patterns on there. I think that's really cool. Okay, I'm going to set that down on a safe spot. This is still hot, as is this. Okay. All right. So now we're going to put this information into the computer program. You could do this with max numbers. You could do it in Excel. I'm going to do it in Google Sheets because that's something that everybody has access to if you have access to the internet. So it's the most universally available, I guess. We're going to start with a blank document. And we're going to put our time, because then we want that on our x-axis, because that is the variable that we control. We decide how short or long our intervals are. And so we're going to put that, because the controlled variable, which is called the independent variable, is what we're going to put in, and that goes on the x-axis. We're going to put that in first. So we're going to put the 0 and the 1. Then I'm going to select both of those. That will tell it that I want to go up by 1 step at a time, 1 number at a time. Then I'm going to drag the blue dot all the way down to the 30, or to the 31, I guess. To 31 because we started at 0. To get us to 30 minutes, because that's how long we took in our first experiment, and the second one was shorter. Then we're going to take our information from the tables that we created, and we're going to put it in there. So we're going to do the one without NaCl first, and we're going to say 1.1, 1.9, 4.0, 6.0, 10.1, 18.9, 24.9, 30, 36.9, 42.1, 47.9, 53.0, 58.0, 63.5, 68.0, 72.7, 77.8, 81.0, 85.0, 87.1, 90.1, 91.9, 93.9, 95.2, 96.4, 98.0, 99.0, 99.8, 99.8, 99.8, and 99.5. And then we're going to go to the next column, and that's going to be the one with the NaCl. We're going to put it in the same times. So at 0 minutes, we were at negative 11.5, negative 10.1, negative 7.5, negative 3.2, 0.0, 7.1, 17.9, 25.8, 33.9, 46.7, 53.5, 59.5, 66.7, 72.8, 77.9, 83.2, 87.8, 91.6, 94.9, 100.1, 101.9, 103.0, 103.0, 103.1, 103.9, and 103.9, and that's where we stopped. Then we're going to go ahead and put in our labels. So this is time, and this is degrees Celsius without NaCl, and degrees Celsius with NaCl. Then we're going to select all the way from A1 to C1 and down to 32. Then we're going to go to Insert. We're going to say Chart. And it's already on line chart. If it weren't, you could go through here and pick the type of chart that you would like. But it is a line chart. You could pick a bar chart, but that's not very helpful for what we're doing. So we pick a line chart. So even though our temperatures didn't do exactly what we had hoped for them to do, it does show something. So it starts out pretty shallow because this is the time where it was melting our ice, because the energy from that heat was going into the beaker and it was melting the ice mostly. It was increasing the temperature a little bit. That largely has to do with the heat coming from the bottom and heating it up quite a bit at the bottom before it moved up. Then we had the ice in the top. So we didn't have a perfect setup, but it does show that it stayed pretty consistent here. Then it climbed quite a bit throughout here. And then at the top it leveled out because now it was going from using the heat, that energy instead of increasing the temperature of the water was now being used to change it from water to water vapor. So what this point shows, that kind of where it starts to climb faster is where we switched and now we didn't have any more ice. And then up here when we started really boiling all the way through. So this one right here is what it looked like without the salt. So this was when we started when all the ice would have melted, and then we started really increasing the temperature. And then around here, it would have leveled off because now we switched. So we're close-ish to 100 when it really levels off. Down here, we're a little bit over, but that again has to do with our experimental setup, not with how chemistry works. Then this one is the one for with the salt. It shows us that our freezing point is quite a bit lower. Then it also shows that our boiling point is also higher because it was right around here that it started. So you can see that. I also wanted to show you one that was under a little bit more ideal conditions where you could heat it all the way through evenly. So I just want to show you that. This would be an example of when it's a little bit more clear. It's a little bit hard to see, but our red line, which is for our NaCl, is a little bit lower, and the boiling point is a little bit higher. So this is a little bit more of an ideal situation where you can see very clearly that right here is where it changed to transferring the heat from changing the phase to actually increasing the temperature. And then here, it really started changing from increasing the temperature to changing phases again. So here from melting the ice into water to increasing the temperature until we started evaporating. So hopefully that helps you understand a little bit more about phase changes. It should also help you understand how we can analyze the data that we gather to actually see what's going on, and hopefully a little bit of help in seeing how you can use something like Google Sheets to create those graphs so you don't have to do them all by hand. Hopefully that was helpful. If you enjoyed today's lesson, please go ahead and click subscribe so you see every time I post a new video, or you can join me over on Skool, where you can join live classes and do these experiments right along with me, or you can check out the entire chemistry course laid out for you step by step so you get a full college prep level chemistry class. I hope to see you soon.